Science 30. I'm going to attempt to finish up the course in this lecture. If not, I'll finish it up in a smaller lecture after this. The last little bit is all about energy transfer. I'm going to talk about some equations. So we ended off the last lecture talking about heat transfer in an internal combustion engine. So we're actually going to discuss the terminology of heat of combustion. All right. So what we're going to do is look at some equations to measure the amount of energy that is released when we, when we break up or build molecules. Okay. And when we look at heat, we're looking at an increase in kinetic energy. Right. So the transfer energy from molecules or atoms at a higher temperature to those at a lower temperature. Right. It's that kinetic energy that makes your engine work. So the heat of combustion is the amount of heat released when a substance undergoes combustion. What we're trying to do is quantify when we break up different molecules, how much energy can be released. So this is called enthalpy, all right? It's the amount of energy that different substances contain. So when we measure heat of combustion, or the amount of energy that can be released from a certain molecule, we can measure that in a calorimeter. If we were in class, we would do a calorimetry lab, but we can't do that. All right, so a calorimeter measures the energy changes of a material. And that's what a calorie is. So when you look at calories in food, for example, what happens is the food substances are burned in a calorimeter. It's called a bomb calorimeter. So it's an isolated system with water, and what happens is the substance is heated and burned. So all of the molecules in the substance are converted to energy, and that energy is transferred to the water. And that's how we get calories. So the amount of energy that's transferred to the water gives you your calorie count for different types of foods. So we can do this with any substance. So the amount of energy required to raise the temperature of 1 gram of water, 1 degree Celsius, is a calorie. And so that's where the term calorie comes from, is when we burn food particles in a calorimeter, we determine how much energy gets transferred. So that tells you how much stored potential energy is inside food. But all molecules have stored potential energy. So that's what we're going to talk about, is how do we quantify that. So this equation, the heat of combustion, this is a modified version of Hess's law that you're going to learn. So this, when we quantify the energy change for a chemical reaction, we're gonna figure out enthalpy of combustion. Okay, or heat of combustion. So the energy change for a chemical reaction equals the sum of the standard heats of formation of the products minus the standard heats of formation of the reactant. So we have determined the energy, we've been able to figure out through calorimetry the energy currency of all these different molecules. And this is in your data booklet. And this is on page 5 of your data booklet. So you take this data of these different molecules, set up an equation, and then you can solve for the energy change in a chemical reaction, right? So these are very common molecules that you'll see in industry or in your daily life. So we're going to measure the energy change in a chemical reaction. So I'm going to take you to page 498 and show you how to do a few of these questions. I'm not going to do all of them. This is number 22 on page 498. So you guys can fill this, you can do this question in your energy and environment booklet that I've given you, right? So this says the following balanced chemical equations are for combustion reactions for each of the fuels tested in the determining heat of combustion investigation. Calculate the heats of combustion for each reaction. So heats of combustion is, again, it's in your data book, it's in your notes here, it's also in your data booklet. But what the equation is, so we're going to look at delta H, and H is enthalpy or energy change. So delta H of a chemical reaction is equal to, this sign is the sum of the number of moles of each products multiplied by the delta H of the products, and we're going to get that delta H, right? So this is delta H. Enthalpy of combustion is a measured. It's a measured quantity. Okay, so that naught tells us that we have a measured standard quantity that we're going to get from the data booklet here. Okay, minus the delta H of the number of moles. Sorry, the sum of the number of moles of the delta H of the reactant. So it's products minus reactants, and we have to take in consideration moles and enthalpies of formation. So the amount of energy required to form these molecules, because that's how much energy is going to be released when they're converted into something else. Okay. So this question says that we have C. Let's look at 22A. So page 498, number 22A. Okay, so this says we have C2H5OH. That's a liquid plus 3 oxygen. And then that makes 2 CO2 plus 3 H2O. Okay, so what we're going to do is to find the delta H of this reaction. We're going to look at the sum of, so we look at the products. So there's 2 times CO2 gas plus, and there's 3 moles of water. So you get that from the balanced equation. 3 times H2O gas. So the state of matter is important here. Okay, so that's my products. Minus the enthalpy of formation of the reactants. Now, elements don't have enthalpies of formation, so you don't, because I'm not making a molecule, so you don't consider elements. So all I have is C2H5OH as a reactant. Okay, so I'm going to take this, my delta H of my reaction is going to equal 2 times, and CO2 gas, carbon dioxide gas, is negative 393.5. And that's kilojoules per mole. So that's how many kilojoules per mole of this molecule is released. Okay, when we convert it into something else. So or form it. And then this is water vapor, so water vapor. So you need to understand, right, if it's H2O liquid, it's not the same enthalpy of formation. So H2O gas is negative 241.8. And then minus, that is C2H5OH is ethanol, so that's alcohol, drinking alcohol. And that's negative 277.6. Okay, and these would all be kilojoules per mole. Okay. So, when we solve for this, we're going to get 2 times negative 393.5. So I have negative 787 plus 3 times negative 241.8. That's negative 725.4. And then that will be plus 277.6 kilojoules per mole for all of these, right? A negative plus a negative is a positive. And my answer is going to be in kilojoules per mole. Of C2H5OH. Okay, so that's going to be so when I do that math, I get negative 1,234.8 kilojoules per mole. So a negative sign means it's an exothermic reaction. So that means when this reaction happened, that right. So when ethanol was converted into carbon dioxide and water, that much energy was released to the environment. Okay, if it was positive, then that would mean that the products gained energy and they removed energy from the environment. So negative just means exothermic, meaning the reaction system release energy to the environment. If we have a positive value with enthalpy of formation, that means that the molecules the system gained energy from the environment, and it would be an endothermic change. Okay? So if I look at B, let's do one more. B says there is 2C4H10, so that's butane, plus 13 oxygen, plus HCO2, plus H2O. Okay, so let's solve for this one. So I actually have 2 moles of C4H10. So that's going to be important when I answer question number 23. So I'm going to leave C for you to do on your own in your booklets. But I'll do the first 2 here. So we have 8 CO2 plus 10 H2O gas. So this is where balancing equations is important if you need to do that, right? Okay, so if I look at the delta H of reaction, you're going to end up with the product. So I have the sum of 8 times CO2 plus 10 times H2O minus the sum of the reactants, and there's no that is an element, so we cross that one out, and that's 2 times C4H10. Okay, so CO2 gas again is 8 times 393.5, negative 393.5. Plus 10 times, it's H2O, water vapor again. So that is negative 241.8. And that's going to be subtracted by 2 times butane is negative 125.7. Okay. Okay. So my delta H of reaction is going to be 8 times negative 393.5. So that is negative 3,148 plus 10 times negative 241.8, which is negative 2,418. And then that's going to be 2 times negative 125.7. So that's going to be plus 251.4. Okay, so when I look at the delta H of reaction for that, so negative 3,148 plus negative 2,418 is negative 5,566. Plus 251.4. And that'll be negative 5,314.6 kilojoules per 2 moles of butane. So that's how much was made per 2 moles of butane, because there's 2 moles of butane in the equation. Okay? And that's what you'll have to do for C as well. You'll get the reaction enthalpy per 2 moles, but 23 says express the heat of combustion per mole. So if I look at 23, I want per mole, so per 1 mole of butane, right? A mole is a measured quantity of a substance, right? It's 6.023 times 10 to the 23rd molecules. So per 1 mole of butane, I would have to divide that by 2. So per mole, so this is number 23, per mole of butane would be negative 2,657.3 kilojoules per mole. So we produce that much energy per 1 mole of butane, but there's 2 moles of butane in this equation, so that's how we get a total enthalpy change of that. Okay, you would do the same thing for C, looking at paraffin wax. So because there's 2 moles, you would divide your answer by 2 to get per moles for question number 23. Okay, So that's enthalpy of formation. This is this helps us explain thermodynamics, right? So the first law of thermodynamics, we have, first of all, we have to distinguish heat from work, right? So work is the movement of matter from one position to another. Heat is a transfer of thermal energy from one location to another. So all work is work, but not all heat produced is work, if that makes sense. So both of them require energy. They both use joules and kilojoules. But if we're producing heat, it's not always used for something useful. It's not always used for mechanical energy. All right, we lose a lot of energy because of the production of heat. But what this tells us is energy of a system can be increased by adding heat, or by having the surroundings of a system do work on it. So you could have energy absorbed by the system from the surroundings. Energy of a system can be decreased by removing heat or having the system do work on the surroundings. So having energy lost to the system. Okay, so there's the environment, right? So what you have to understand is that when we look at thermodynamics, there is a reaction system where the chemicals are reacting, and then there's the environment around it. Okay, so if work goes into the system, that would be called endothermic, and that would be positive work. If energy leaves the system, that would be exothermic, and that would be negative work. Now, we perceive this in the environment as two things, right? So what happens is, because we exist in the environment, right? We don't exist outside. We don't exist within a reaction system with chemicals. What would happen is if a chemical reaction created an endothermic change, the environment loses energy, and we would perceive that as a temperature loss. Likewise, if a chemical reaction system released energy to the surroundings, and the environment gained energy from a reaction system, so as the chemicals reacted and released energy, we would perceive that as a heat gain. Okay? Okay, so the first law of thermodynamics tells us that it's a restatement of the law of conservation of energy. The total energy, including heat in a system and its surroundings, remain constant. So whenever heat is added to a system, it transforms into equal amounts of other forms of energy. So we can use heat to do work, but the amount of energy present before a reaction needs to equal the amount of energy present after. Okay? So energy cannot be created or destroyed. It's just like matter cannot be created or destroyed. But it can be converted into something else. Okay, the second law of thermodynamics is about transfer. So heat always travels from an area of high concentration to low concentration, right? So heat high, right? So it's the same thing as matter, right? Matter always diffuses into areas of low concentration to be in a lower energy state. Okay, so flow never happens naturally from a cold object to a hot object. Warm energy always, right? So places of high energy, which would be warmer, move to places of low energy, which would be cooler. And this explains how heaters work. This explains how air conditioners work, right? We have to, if we're going to use air conditioners, we're going to have to move, right? We move heat out of an area that we don't, right? So we want to move heat out of a house, which is we would move heat into an area where there's already high heat, which would be outside in the environment, and that's why air conditioners require energy. Okay. So if you think about a natural system, think about all the energy conversions that are going on, right? So you have solar energy, and then we're converting that solar energy into chemical potential energy in the form of glucose, right? That glucose is used to make ATP, so that's another energy conversion. So that chemical potential energy is converted into mechanical energy, and then that ATP in living systems, right, is used to do work in the body. So create thermal energy, create kinetic energy, create sound, create movement, do everything that a living organism needs to do, right? So think about this. Think about all those energy conversions, right? Solar to chemical potential to mechanical and sound and all those other types of energy, okay? So that's what we're talking about here is energy conversion. Right, so these are all your different types of power plants. So think about energy conversions in this power plant, right? You have stored chemical potential energy converted to kinetic energy, which is then converted into electrical energy, right? So this water moving through the penstock turns the turbine, and then the turbine moves to an electromagnet and creates electricity. Okay, right, so page 500, which I've already addressed in the previous unit, you need to look out for this unit. Okay, a coal-fired generator does the same thing, but it has stored chemical potential energy. It doesn't have stored water, right? And then this coal is burned, and that heats water up and turns it into steam, and then the steam condensing is what turns the turbine. Nuclear power splits atoms. We're trying to fuse atoms in the form of fusion. We'll talk about that in a second, but it does the same thing. When we split atoms, it releases a ton of energy, and it'll heat water, and that'll turn a turbine when it changes state. And right, so it all works on the same principle. So your armature in a power plant is the turbine. Okay. So I'm going to shift gears here. Again, we're going to look at energy creation again. We're going to talk about harvesting nuclear energy. I'm going to talk about alpha and beta decay. And I'm also going to talk about E equals mc squared, so energy having mass equivalency. Okay, so nuclear energy comes from the release of energy from the breaking or fusing of atomic nuclei. So a proton is a component of an atomic nucleus, right, and has a charge of 1 plus, or 1 atomic mass unit. A neutron doesn't have a charge, but it has the same mass as a proton. An electron is a wave. It's a wave particle, but sometimes it acts as a wave and sometimes it acts as a particle. So electrons are electromagnetic radiation and matter at the same time. So electrons don't have necessarily registered atomic masses. We'll talk about that. So protons and neutrons exist in a nucleus, so they're called nucleons. Electrons are outside of that in quantized orbit, right? Okay, so just as a reminder, atomic number, right, is the number of protons that are present. This is the atomic mass. So this is the measure of the amount of nucleons in a nucleus, so the amount of protons and neutrons. Now, you have decimals on the periodic table because this shows the average of the mass of all the isotopes of these objects that exist in the environment. So an element that's helium will always have 2 protons, but it might not necessarily have 2 neutrons, right? If you change the amount of protons and you change the atom, but you could have the helium could have 1 proton, it could have 2 protons, it could have 3 or 4 protons. It depends on the isotope. So this is the average mass of all of the isotopes that exist in nature. Okay, so for the most part, right, so the atomic mass is the amount of protons and neutrons combined. So for the most part, helium has 2 protons and 2 neutrons, but there might be some cases where helium has 3 neutrons, and that gives this extra mass here when you average it all out. Right, we're able to quantify amounts of mass in the universe based on stellar and the anatomy of stars. Okay, so that's the atomic symbol, but these are isotope symbols. So isotope symbols, you're actually going to see numbers on the left, okay, not on the right side or top and bottom. This is an isotope symbol, and what you're actually going to see is the larger number on top, so the mass number, and the atomic number is the number of protons. So when we talk about radioactive decay, this is going to be what we're looking at. Okay, so isotopes are atoms of the same element that can have a different number of neutrons. So remember, ions are matter that has a different amount of electrons, right? You get a positive and negative ions, but isotopes, we don't change the charge, we change the mass because we change the number of neutrons. So mass number is the number of protons and neutrons added together to give the weight of an element. And the number of neutrons is found by subtracting atomic number from the atomic mass, because the atomic number is the number of protons. So whatever is left over from the mass number will be the number of neutrons, right? So mass number minus atomic number equals the number of neutrons. Okay, so when we create nuclear energy, we split an atom, right? So we have the strong force called the nuclear force, and that's the attraction of particles within the nucleus. And that could be proton to proton, neutron to proton, or neutron to neutron. There's a very, very, very strong attraction between these particles. So it takes a lot of energy to break them, and therefore a lot of energy is released. So when repulsive electric forces between positively charged protons are strong, the nucleus can break down and release radioactive particles. And we call this radioactive decay. So really what's happening is when we destabilize the nucleus of an atom, we'll release particles, and the particles, some of them will be converted straight into energy. All right, so these particles are spaced apart from each other in a cohesive fashion. When we do something like smash a very high energy particle into an atom, we can destabilize it and break it. And then some of the particles will decay or be converted into energy, and that will release electromagnetic radiation. There may also be some of these atoms in a nucleus that is undergoing nuclear fission, or the breaking of an atom might be converted into other atoms, and that also releases energy. So the presence of neutrons to dilute the electric force of these protons stabilizes the atom. So when we start knocking neutrons out of atoms, then what happens is the electrons start to repel each other, and that will destabilize atoms. So unstable isotopes with differing number of neutrons can cause unbalanced forces within the nucleus, and that creates radioactive decay. So on your So I'm going to talk about alpha decay, and there's also beta decay. Oops. So we'll talk about those two, but I want to start on page, so page 502 is where this nuclear radiation stuff starts, and page 503. Okay, so you have questions 26 through 28 to look at. I'm going to look at this green table here on question, that's question 26. So page 503, number 26. So it's asking, so I have an isotope of hydrogen. So this is hydrogen 2. So you need to have your atomic, you need to have your periodic table here. Okay, so this is a hydrogen 2 isotope. So H2. Okay. So it's asking what's the atomic number. And I know what the atomic number is. The atomic number is right here. Okay. So the atomic number is 1. The mass number, so if it's an isotope, I get this. So the mass number is 2. Okay. When we look at the number of protons, hydrogen always has 1 proton. Okay, hydrogen will always have 1 proton because the atomic number tells us that. It has in a deuterium isotope, it has 1 neutron because you have to add up protons and neutrons to get mass number. So the number of nucleons it has is 2. Okay, let's look at carbon. So the next one on that page is carbon 13. Okay, So the atomic number of, so this is a carbon-13 isotope. The atomic number of carbon is 6, okay? The mass number, it's giving it to you because that's its isotope number is 13. The number of protons that are present is the same as the atomic number. There's 6. The number of neutrons is going to be mass number minus atomic number. So 13 minus 6 will equal 7 neutrons. And the number of nucleons is 13. Okay? So that's number 26 on page 503. All right, so you can fill that in. I'm going to look at number 28 as well. You can do number 27 on your own. Number 28 says, using nuclear notation, express the following isotopes. I'm going to look at uranium-235 and uranium-238. So when I look at the nuclear notation, I'm going to look at isotope symbols. That's what it's asking, is make the isotope symbol. So uranium is 92. Okay. Uranium is 92. So here's how I write this. I'm going to write it's U235, the first one. So 235 is the mass number, and then I write the atomic number under it. Okay. Nuclear notation for uranium-238 would be this. U-238, and it still has 92 protons. So I would subtract the atomic number from the mass number to get the neutrons. So you can, right, so U-238 and U-235 don't have the same number of neutrons, right? U-238 would have 3 more neutrons. Okay. Alpha radiation starts on page 504. Okay. So here's what happens. So with alpha radiation, a stream of alpha particles is produced from unstable nuclei. An alpha particle is a positively charged particle consisting of 2 protons and 2 neutrons. So what happens is when alpha radiation occurs, a helium atom is produced as a product. And so an alpha particle is a helium nucleus. So page 505 kind of walks you through this. All right, so you can look at that, but I'm going to do this example on page 505. You can see that we use americium, the decay of it, so it naturally decays over time. We know what the half-life is, and we can use that for smoke detectors. Okay. So americium, this is page 505. This is a practice example. If we have americium-241, and it has an atomic number of 95. Okay, it undergoes alpha decay, and that's what the question tells us. So automatically